fine. Okay. So, not much is left, not even 1.5 hour class as it turns out, maybe I should have gone slower. So, we close today with a brief discussion of what are reducible representations and what are irreducible representations. You know this already, but we need to know we need to know how to denote this. So, that is going to come handy later on when we go into further discussion. So, this is how we generally denote the representations. Which letter is this? Gamma, right? Gamma, capital gamma. So, we generate representations by gamma. Let us say gamma is an n dimensional representation of a group of transformation operators OR acting on a basis F1, F2, F3, so on and so forth up to Fn, right. And let us say, this is not a general case, let us say this is what the situation is. What is OR F1? OR F1 equals D11R F1 plus D21R F2, and by now I think we are familiar with this notation. It is not D12R, but it is D21R because we are working with the basis. D21R F2 plus so on and so forth DM1R Fm. So, what I am saying is that these D's, dxy's, they can be 0, they can be non-zero, general. But then we have plus 0 into Fm plus 1 plus 0 into Fm plus 2 etc., up to plus 0 into Fn. And a similar pattern holds for ORF1, ORF2, ORF3, so on and so forth up to say ORFM. Have we encountered a situation like this? So, when we work with XYZ and we said that the principal when we say that there is an axis of rotation along Z axis, then what happened? Did we not get a similar situation? X and Y mixed, Z did not, right. So, X dash was, what was it for rotation by theta? Huh? Okay, you can work it out, right. Sin theta or cos theta multiplied by X, X dash equal to cos theta or minus cos theta? Cos theta, then plus sin theta or minus sin theta y. So, you can work that out. Then plus what into Z? 0 into Z, right. Similarly, for y you add something into x plus something into y plus 0 into Z. So, this is a just a general depiction of a similar situation. The coefficients of all the functions beyond Fm are 0 for the transformed functions F1 to Fm, ORF1 to ORFM. Okay. Let us say it is like this. It is just an extension of what we had for x, y and z. So, basically some functions by the operation R, some functions are mixing and some others are not. So, we say that these do not contribute to the first ones, alright. Let us say this is the situation. What we are trying to do now is, we are trying to see what a reducible representation means, okay. And then let us say the situation is like this. OR Fm plus 1, we do not know what the coefficient is. Let us say everything is non-zero, 0 non-zero whatever it is. Let us write d1 m plus 1 r f1 plus d2 m plus 1 r f2 plus so on and so forth, plus what will be the last one, dn m plus 1 r fn, and last one is this. OR Fn is d1n r f1 plus d2n r f2 plus so on and so forth, dmn r fn fm plus so on and so forth plus dnn r fn. Okay. Let us see whether these are 0 or not, we will see. Okay. So, now I want to isolate the zeros, so I will draw these two lines. So, then this is a 0 block, this is a non-zero block. What are these? we will see. Okay. Now, this is an equation that we are very familiar with now, ORFK equal to sum over j djkr fj, right, and we know that the way these coefficients are arranged, that is really a transpose of the way they are arranged in the matrices, right, because we are working on the functions, the basis. So, this is D11, D12, D1m, should they be down a column or should they be along a row? It should be along a row, right, that is what I am saying. Now, what is the dimensionality of this block? M by m. What is the dimensionality of this block? M plus 1? N minus m into m. Is it n minus m into m or is it m into? Are you talking about the matrix or are you talking about what you get from here? It is n minus m into m. How many elements will be there from here to here? This is n, this is m, so this is n minus m, right? Now here we are going down, but in the actual matrix we will be going from left to right, right? So with respect to the transformation matrix, it is n by m into m, n minus m. So as far as the transformation matrix is concerned, it is a n minus m into m block. Okay. What is this? What is the dimensionality here? M into n minus m, and this is definitely a 0 block, isn't it? In the matrix all elements will be 0. What is the dimensionality of this? N minus m into n minus m. Good thing is that there is no confusion whether it is matrix or whether it is the operator. N minus m into n minus m is the same as n minus m into n minus m. Okay. So what will the matrix look like? Let us just get rid of everything else and write the matrix. This is what the matrix will look like. We have a block here m by m, this is m into n minus m, n minus m into m, n minus m into n minus m. Alright. I call this block, let us say D1R block, just naming, this is very easy. Now where is the 0? Here or here? Here or here? Here, right, because we have transposed, do not forget. So this is a 0 block, definitely. I call this the Q block, we will see what Q is in a moment, and I call this the D2R block. So the matrix can be divided into 4 blocks, right. So this is the same matrix, just written in a more sane size, right, 4 blocks. And do not forget that we are talking about an n dimensional representation and we are talking about the f functions, alright. Now let us say that the f functions are orthonormal. If the functions are orthonormal, what will happen to the matrices? They will be unitary, right? The DRs are unitary. So if DRs are unitary, then you know what that means. D of R inverse. What is D of R inverse? The transformation matrix of the inverse of R, inverse operation of R. So if you are talking about a C3 rotation, then it is C3 minus rotation or C3 square rotation, fine. So dr inverse equal to dr inverse equal to dr transpose. I think this is something that we have discussed earlier also, right. So now this is dr transpose. Okay. All that happens is that this 0 and q get interchanged, isn't it? Now the thing is this, what is dr transpose? Dr transpose, as you told me right now, is the transformation matrix corresponding to the R inverse operation. Now see, do you think R and R inverse are going to mix functions differently. What R has done is that as a function of R, we have seen that there is no contribution of f m plus 1, m plus 2 etc. up to Fn in F1, F2, F3 and up to Fm. So, do you think that in the R inverse operation we are going to have contribution from this Fm plus 1, Fm plus 2 etc. up to Fn elements in the transformed F1, F2, F3 up to Fm elements? It is just inverse, right? So, it is not possible that the function does one kind of mixing not function, it is not possible that the operation mixes a given subset of functions and the inverse operation mixes a different subset of functions. That is not possible, right? Right? What will be different between plus and minus operations? The coefficients, right? Coefficients will be different, but for F1, F2, F3 up to Fm, the subset of the basis that is being used, that cannot be different. Right? So, what does that mean? Q is 0, that is what it means. So, Q equal to 0. Okay? So, I put in 0. So, now see, these matrices are block factorized in a certain manner. This D1R and D2R are the two non-zero blocks. These two are definitely the 0 blocks, right? Can this also be a 0 block, D2R? So, if it is 0 block, then what will be OR Fm plus 1, or let us say what will be OR Fn? We have already said that for OR Fn, this front block is 0, right? 1 to m do not contribute to our Fm, Fn, sorry, what am I saying? Right or wrong? We have proved that Q block is 0. Where did the Q block came from? Contribution of F1 to Fn, F2 to Fn, so on and so forth up to Fm to Fn. Those are all 0. Now, if the contribution of Fm plus 1, Fm plus 2 dot 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 Fn, these are also 0, then what kind of operation is OR? Do you understand what I am saying? So, you have just proved that Q equal to 0. What is Q? Contribution of which functions in which function? Okay, what was the 0 block that we started with? I will go back. What was the 0 block? It is a contribution of Fk or Fi, where I equal to m plus 1 to n in Fj, in OR Fj, where j is 1 equal to m, j equal to 1 to m, right? Now, this is the other block. This is the other block, right? This is a Q block. What does the Q block stand for? Contribution of F1 to Fn, F2 to Fn, F3 to Fn and so on and so forth. That has been proven to be 0. Now, if this block is also to be 0, that means none of these original basis functions makes any contribution in the transformed function, right? Or in other words, if everything is 0 here, OR Fn equal to what? 0. So, what kind of an operation is OR? It is an annihilation operation, that is right. Annihilation operation is definitely not a symmetry operation. Okay, so it cannot be a 0 block. Some of the elements can be 0, fine, but at least one has to be non-zero. No? In A2 block, this is the A2 block, isn't it? Why do you say that? I am saying that the block cannot be 0. If it is 0, then of course the determinant is 0. At least one non-zero element in each row is required. So, and that single non-zero element will prevent it from being a 0 block. Even if there is at least one non-zero element, there cannot be even one row that is completely 0. Yeah. So, every row must have at least one non-zero element, right. So, A2 cannot be a 0 block. D1R is a block, D2R is another block, and these off diagonal blocks are the 0 block. What do you call a matrix like this? It is a block factorized matrix, right. This is called a fully reducible matrix as well. Okay. So, what is a reducible representation? A reducible representation is a representation in which all the transformation matrices can be block factorized in an identical manner. To start with some dr, you should at least be able to perform some kind of a similarity transformation in such a way that all of the matrices become block factorizable in a particular way. And this is something that we have done already before going through all this, right. We block factorized every matrix in the same way, remember. Say for example XYZ again for C3V or C2V, which one did we do? C2V perhaps, C2V. For C2V what happened to XYZ? We block factorized in such a way that we had 3 1 by 1 blocks, right. But then when we took the atoms, then we got 1 1 by 1 block and 1 2 by 2 block, right. So, we block factorized in the same way. It is not that you are going to put the lines, you cut off the last row and the last column in one and cut off the first row and the first column in one, no. You have to block factorize in the same way, right. So, then it is a reducible representation. If you cannot draw the lines like that, even after performing similarity transformations to your Hertz content, then it is an irreducible representation. Then it is an irreducible representation. This is a formal definition. A reducible representation is one in which all the matrices can be block factorized in a particular way. Now, the matrices as such may not be block factorizable, but there should be some similarity transformation that you can do that will make them all block factorizable in the same way. If that is possible, then the representation is reducible. If it is not possible, then it is irreducible, right. Okay. And this is how we write it. Let us say this is a reducible matrix. Okay. So, here we have all these diagonal non-zero blocks, off diagonal blocks are all 0. Okay. This is how we write it. Gamma equal to gamma 1. What is gamma 1? Gamma 1 is the collection of the D1R blocks. What I am saying is that for all R's, for all symmetry operations, the matrices should have the same form. Okay. So, collection of all the D1Rs is called gamma 1. Should I write gamma 1R? I am writing D1 and then R in bracket. Why will I not write gamma 1 and R in bracket? That is a silly question. Why will I not write R for gamma? Yeah, so I have taken all the R, so why will I write R? Huh? See, the matrices, you have one matrix for every symmetry operation. That is why you have to write R in bracket, that means it is a function of R. But then when you are talking about the representation, you have taken all the R's, you have to look at all the R's at the same time. So, there is no point in writing R in bracket anymore. So, this is how we write it. If this is what the matrices look like, then the representation gamma is gamma 1, I will just call it plus, but just to show that it is not really addition, it is plus inside a circle. I do not know what it is called. Does anybody know what this sign is called? If we do a multiplication inside a circle, what is it called? Huh? Yeah, convolution. It is also called convolution. So, this is just to denote that all these, so this plus inside circle means you are adding blocks. So, you can do not just add them, do not add d1r to d2r, have d1r, put in the zeros, then put d2r in its place. Okay. This is block addition. Gamma equal to gamma 1 plus gamma 2 plus etc. plus gamma n. Okay. Now, it is possible that gamma 2 might be the same as gamma 3, or there might be 3 gamma 2s or 3 gamma 4s or on. So, the general case is gamma equal to sum over ai gamma I. So, that is how we write the representations. A reducible representation is a linear sum of smaller representations, and generally we take these gamma i's to be irreducible representations. So, what we say is that a reducible representation is can be constructed, it should not be a reducible representation can be written as a linear sum of irreducible representation. Just remember that when I say linear sum here, I mean that I am doing block addition, I am not just adding up matrices just like that. Okay. So, this is the definition of reducible and irreducible representation.